Unit 7.5. We'll be working with searching. Searching an array for a particular data point. Now, what I'm going to do here is I'm going to go a little bit beyond the AP expectation and look a little bit into big O. Big O runtime. So I'm not necessarily going into depth with this. Years ago, we used to go into real depth with this. I know some people are not taking calculus yet, so some of this stuff might be a little bit beyond your ability. So I'm going to try to keep this somewhat informal, but I'm going to point to a couple of things that go on when we're talking about how fast is this algorithm. Now, the first thing is, you could say, well, why don't we just time them, right? Why don't we just put a stopwatch and run it and time it and see how fast it is? That could work as some kind of information, but it's a little bit unreliable. It's a little bit unreliable because one computer may be faster than another. There is some bias built in there because this computer is faster, so you run the algorithm faster. When the algorithm itself is not as fast, then one computer may have too much stuff on it, so it's bogged down and it can't really execute it as fast. Or, we have a lot of different things, and the human error in the timing, and so we have uh, other ways to do it. We could count. We could say, oh, let's just count how many times this thing runs, and do a counter and count and count and see. Um, that's one way we could do it. But the best way to do it is using a mathematical technique called Big O. It's based on limits. So if you've never done limits before, if you've never done calculus before, this will be new. But it's basically a limit as n, which is called the input size, goes to infinity, and we do what is called a growth rate comparison. So there is this f of x over g of x. It's mathematical. And then we look at it as to what happens when the input size increases. Now, I said the input size, and you may wonder, what does that have to do with anything? Well, let's think video games. If you're on a video game and we have, let's say, 100,000 people online playing all at the same time, that game you think should get slower or so on if 10 million people jump on the game. Well, the idea behind algorithm is that we don't want the game to show any effects based on the input size. Like if I have 100,000 people playing the game or 100 million people playing the game, it's the same. Nothing changes. Okay, that's tough to do, but that's what we try to accomplish because we don't want the input size affect performance. So when we write an algorithm, we have to think about, is it true that this algorithm could sustain a larger input size, or would it slow up tremendously and cause the app to be behaving strangely? So this is what we're looking at. So I'm going to go ahead now and jump into Big O. Not as, it's going to look scary if you never did this before, but I'm just going to show this, and I'm going to go into it too much in terms of what goes on here. But here's the LIM stands for limit, and it says x goes to infinity, and x in this case is the input size. And what they're showing here is the growth rate of two functions, f of x over g of x, and equals 0. They're the same, something like that, going towards infinity, or it's greater than 0. So this is the mathematical look of it. I won't go into it too deeply because there's no need. The big O notation is definitely mathematical. All I'm showing you is that it does come from math, okay? I don't want to go into this, especially since some people have no idea what these things mean. But what I do want to point to is because it's mathematical then, and we can't necessarily all guarantee that we understand these symbols and stuff like that, what I'm going to do is show you how this looks informally. Okay, so I'm going to go to my next slide. So this is how we think about it. Okay, we think about it, and you can see the g of x, and well, they have n here. They actually have the n's instead of x. Those were more mathematical. In computers, we use n. Input size, you see, input size on the x-axis, okay? And the behavior of the algorithm is plotted, okay? So, for example, if you're looking at g of n, you could see here it's kind of going up here, okay? And g over here is kind of going up somewhat, and we have some other information here and so on. Now, what this is really saying is that the worst case scenario, the best case scenario, and the average case scenario is what we consider the time complexity and asymptotic notation. So basically, all we're doing here is saying this algorithm has three ways to look at it. We could look at it as how it's behaving in the best case. Okay, what's the best case? How fast is it? Averagely, which is the one that we use most often. The average is how do we figure out how it behaves normally. And the worst case, when this thing is really under stress and having a tough time. So we look at it that way. Okay. Now, what I'm going to show you next is the big O notation in a graphical way. Now, I show them here in graphical way because we look at these three things. So I'm going to give you a quick example. So let's say we are looking for a data point in an array. Let's say we're looking for the number 6 in a list of integers, right? The best case scenario would be if 6 is at position 0. Why? Because we look at 0, we spot it, we got it. Done. That's fast. The worst case scenario is if that 6 is at the very end, and let's say we had 1,000,000 of them. Well, we'll have to go through and check if we're doing a linear going through the entire list, and then we find at the end, well, that's going to take long, right? That's the worst. The average case, it's somewhere in the middle. Well, not necessarily exactly in the middle, but somewhere around there. So we could kind of say, okay, we expect it to be this fast. So that's one quick example. Now, in graph terms, we could look at them this way. That one I just spoke of is called this guy, the blue line. It's called ON. It's called linear time, meaning this is an algorithm that has a list, and we're going to look through every single one till we find it. This is called an n squared algorithm, which we will see. This is a parabolic, right? It's like half of the parabola. The next half would be over here somewhere. This algorithm here comes from generally nested loops, a for loop inside of a for loop, which is what we're going to see. Now, this is not on the AP exam per se, but they said to do it informally. But let's just take a look at it a little bit more than just informally. So this is a graph that represents an n squared algorithm. And so this is the one that we are accustomed to, linear things, you know, straightforward. If the input size increases, the time is longer, right? If I have 10 things in a list, then I'm going to find them fast no matter what. But if I have 1,000,000 things in a list, then obviously this is going to affect how fast it is. And same with here, right? This is crazy because once this get 1,000,000 things, got 1,000,000 squared, that's going to take a long time. Log n is what we normally get when you have a very good algorithm. This is log base 2, okay? And if you don't know what logs are, you could think of it as successive division. All right, so the way it works is log base 2 of 8 is 3 because 2 to the third is 8. Log base 2 of 16 is 4 because 2 to the 4 is 16. So the base is 2, and we raise it to a power, just like we did with bits. Raise it to a power, we get a number, and then so the log base. So we're saying then is that as the input size go bigger, it doesn't take that much longer, right? It's almost straight across. Okay, it takes a lot to make this go up. However, O1 time, this is called constant time. This is what we are trying to achieve. Every algorithm we want this time. It means if 10,000 people are playing the game, or 100,000 people are playing the game, or 10 million or 100 million, the game is the same. The input size has no effect on the time. The game works just as fast as a small amount of people on or millions of people on. Okay, that's what we're looking for. So this is an informal view. So what I'm going to do now is go to the algorithms for searching. And the first one is the linear search, the same one I spoke of. We process all of them at a time. It's ON. And then we have another one called binary search. And this one is O log n. So how does this work? You use a sorted list. So the key for binary search is that the list has to already be sorted. Linear search don't have to be sorted. It could be completely random. So if it's a sorted list, we're going to repeatedly look in the middle of the list. And if we don't find it, we're going to make a decision as to go right or left. And based on that decision, we're going to look in the middle of that sublist. I'm going to keep looking in the middle of the list and the sublists until we find the thing we're looking for or we don't find it. So here are two examples. The code is written. Linear search. This is the algorithm for linear search. It has the array. I'm using integers, but we could use anything. The same idea here. We just change the type. So we have an array of integers and we have looking for a target here. And what we're going to do is we're going to look through every single one, starting at 0, stopping at length -1. Remember, it's less than, so we're stopping. When we get to length, it's over. Last comparison would be at length -1. I'm looking, is it true that this guy that I'm looking for is the guy that's at the spot? If it's true, return this method is over. If this is finished, normally what we do is we send back the index as to where the actual value is. So for example, if I'm looking for the number 1, this guy, it's going to go here. Is it a 1? No. That's what this is asking. Okay, go over plus plus. Is this a 1? No. Is this a 1? No. Is this a 1? No. Is this a 1? Is this a 1? Is this a 1? Until we find the 1. When it finds the 1, it's going to send back the index where 1 is. 0, 1, 2, 3, 4, 5, 6, 7. It's going to send back a 7. Now, if a 1 was not in the list, it will go and it'll go to the end, and then it'll send back a -1. That's what we usually do. Since -1 is not an index in any index structure, the lowest is 0, -1 means not found. Moving on down, this is not necessarily sorted, okay? So it doesn't have to be sorted, but this one needs to be sorted. And I'm saying it's the iterative solution because later in the course we're going to do recursion and we're going to do a recursive solution for this. So right now I have this list here, and this is the example. It's sorted. It's 12, 21, 35, 42. It's sorted. So I'm looking for the number 21. Well, let's see how this works. So the first thing is it has this high, low, and middle. 3 pointers, 3 indices that I'm going to use for pointers. And I have whether it's found or not, obviously, because I might not find it. But I'm going to look for the number 21. It will be found. The first thing that happens is we figure out where the high point is, which happens to be length -1. So we are pointing at 103. That's where the high is right now. Low starts off at 0. It's at 12 right now. So we have 3 pointers. Then we calculate the middle. Is the value of this index plus this index divided by 2. That's the middle. So we're at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we're going to take 0 and 9, add them, we get 9. Divide that by 2, we get a 4. Be careful here. We get a 4. Not a 4.5. This is an integer. So we got a 4. 0, 1, 2, 3, 4. So we have 3 pointers. The middle is pointing at 51. Low is at 12. High is at 103. And then we make a decision. This is going to run in a loop. And as long as the middle is less than the high, we can run it again. So we get the middle value, okay? So we had 51. We say, is that the same as 21? It says no, okay? So we didn't find it yet. Okay, decision time. Are you going to look on the left or are you going to look on the right? Well, it all depends. The question is the number we're looking for smaller than this? And if it is, to go on the left. If the number we're looking for is bigger than this, then go on the right, okay? So what I do is take the middle guy here and say, okay, is this the same as the number? No. Is it smaller? Yes. All right, we're looking over here then. So keep the low where it is. Okay, so we're looking on the left. See, I have it. Keep the low where it is. Okay, don't update the low. Okay, but do update the high. So the low stays here, and the high who used to be here is now at 51. Right? Some people will say, oh, well, we could have subtract 1 and put the high at 42. True. But it doesn't really matter because this algorithm cuts it in half, if you didn't realize. Successive division by 2, because the fact that, it was not on the right side, this is literally half the array. Now, let's say this was a million things. That means on the first run, if we don't find it, we'd eliminate 500,000 things. Half gone. I'm not going to look at that half because it's not there, right? So this is much faster. That's why it's log n. Now, because this is at the 51 and the low stays where it is, the middle needs to be recalculated now. So the middle is going to be 0, 1, 2, 3, 4, right? 4, and then you add that to 0, divide that by 2, I get 2. So 0, 1, 2. So now my middle is at 35. It says, hey, is that the guy? No. All right, is it less than that? Yes. So now I'm looking on the left. I'm over here. See, got rid of half again. Leave the low where it is. High goes to where the middle was, 35. Now I'm going to recalculate. Now the middle is going to be 21. Is that it? Yes, found it. Once I find it, I send it back. The middle index, which is 0, 1. So we're sending back saying the 21 that we're looking for is at position 1. And that's the end of this algorithm. Now you can tell how this is written, okay? There's a while loop that says, well, the middle has to be less than the high. That makes sense, okay? Because the high can't be on the left of the middle. That doesn't make any sense. So it's going to be low, middle, high. So the middle always has to be less than the high. So that's when that is not true, it's going to stop, and we didn't find it. So once we looking here, we look, the first move is always to look to see if we found it. And if we didn't find it, the decision is, are we going to the left or are we going to the right? So here's how it works. Is that the target is less than the value, we're going left. Exactly what we had, right? We went to 51, and then 21 was less than 51, so we moved to move left, and we came over here. Okay, and that's pretty much how binary search works. And the linear search, you see the difference? This one looks for everyone, this one chops it up in half and keep looking in the middle. All right, so what we're going to do now is run these two and see if we got the right solution. I'm going to run it for 1, and I'm going to run it for 21 and see if we find it, okay? So 0, 1, 2, 3, 4, 5, 6, 7, and 0, 1. So we should get a 7 and a 1. Let's scroll down to the end, and let's run that. So here is my 7.5, and here is the first one that says do a linear search, look for the number 1. It's a static call, okay? Like I'm putting all this stuff back together, keep that in mind. Unit 7 dot. And this one here is looking for the number 21. We're going to run that. So there's a lot of stuff printing. Let's see. Here we go. 7 and 1. We found them. This is a little bit of information surrounding the big O notation. Just a little bit. Nothing too much. We didn't write a whole lot here. We did make a big informal push of these algorithms, okay? So how fast they are, and I'll show you them one more time just to wrap up. This guy here is the informal look. Along with him, okay, the idea of the best case, worst case. Same thing is true for the binary search, right? The best case would be it was in the middle, right? As soon as I looked in the middle, I found it. Best case, right? Worst case for the binary search, though, is going to be, it's going to be somewhere in one of those halves. And the thing is, because the binary search is so fast, the average and the worst case happens to be pretty much the same idea here, because it's a sorted list. The math does support it, but some of us don't do this level of math, so it's not necessary to go too deep in it, but it does depend on a limit, and all we're trying to do is increase the size to infinity. That's all we need to walk away with from here. Now, one thing with these searching algorithm, we do measure how fast they are, but we also do measure how fast a sorting algorithm is. So the binary search has one additional piece on it, that it needs to be sorted before it's done. So we have a little extra time there for sorting, but it pays off because the algorithm for searching is that fast. Again, we have a linear search, which is of order n, looking each one. Binary search, chopping in half until we find the right one in the middle, or maybe it's not found and we send back -1 as the index. That brings us to the end of 7.5.